Good afternoon, everyone, and good morning for the people in the center and the west. Um, my name is Anand Padmanabhan, and I'm a research associate professor in the Department of Geography and GI Science at the University of Illinois Urbana-Champaign, and I'm serving as the managing director of I-GUIDE. So today we are conducting what's called the VCO series, the virtual consulting office, which we do on a weekly basis. And today's topic is on mapping wildfire threats to transportation infrastructure with spatial AI. We have three presenters today: Shaun Williams, um, Carey Whitehair-Conde, and Jeremiah Huggins, all of them from CNA Corporation, and all of them were participants and winners of our the spatial AI challenge that we conducted last year as iGuide, and they will be presenting the work that they did as part of the challenge and maybe even broader. So let's take a moment to welcome all of them, and I'll pass on the baton to Shaun. He's going to be our lead presenter. Shaun, take it away. Shaun, you're muted.
Okay. Yeah, my apologies for that. The control panel wasn't displaying for me. So I really appreciate the introduction, Anand. And speaking on behalf of Team CNA, it is our pleasure to have the opportunity to present our project to you today. And just a little background about our organization. CNA, it is a nonprofit, nonpartisan research and data analytics organization based out of Arlington, Virginia. And Carey, JJ, and myself, again, we are quite happy and excited to have this opportunity to present our work to you today. And as Anand noted, one of the reasons why we are sharing our project with you today is our second place finish in the 2024 iGuide Spatial AI Challenge. And one of the benefits from placing second was that a few members of our team earned the opportunity to attend the iGuide Forum in person in Chicago earlier this year to receive our award and also speak on our research. And there I am in the center of the picture, and to my left is Carey, and to my right is another team member by the name of John Chrisman. So for today's agenda, simply stated, we're going to walk you through the process of how we leverage GeoAI to reveal wildfire threats to roads and rails. So more specifically, we're going to begin with like a higher level overview of our project and provide some context into why the wildfire threats to transportation infrastructure really matters. And then we're going to follow up with providing some details, introductory details into our AOI and why that was selected, and also explaining the data sets that we utilize throughout our project. And from there, we're going to pivot to discuss how GIS was applied for training labeled data sets, and then Carey's going to discuss our UNet model, including why it was selected and how it was implemented to generate the pixel level wildfire threat predictions. And we'll conclude by highlighting our outputs and validation processes before closing out with covering some of the real world applications, some of the interesting takeaways that set up the next potential steps for our work to go. So, in terms of wildfire threats to transportation infrastructure, so there were a myriad of reasons as to why this was such a compelling topic for our team to explore. First and foremost was the recognition that roads are really lifelines in fire zones. They're how people evacuate and how responders get into areas of need, and how supplies, the critical supplies, can move around. And wildfires, they obviously have the ability to cut these lifelines. So the map before you, it shows a small yet notable selection of fires that have trapped evacuees, forced people to flee on foot and abandon their cars, and even closed highways for weeks on end. The map also illustrates that this just isn't a Western state issue. So, for example, fires in Tennessee and New Jersey, they've showed that road vulnerability to wildfires, they exist across the United States. So we chose this topic because it connects safety to resilience. It's not just about the fires, but how the wildfire threats can ripple through so many aspects of our society, from evacuation planning to emergency management and even to the economy. So think of it like this. The fires themselves, they show like what can happen, but as a team, we wanted to ask, like, where else could this happen? So that's why we leveraged spatial AI with the UNet model in hopes that our model could become a tool to detect and map wildfire threats to roads and rails, your transportation infrastructure, before the next crisis. So we picked this topic because roads, they can fail during wildfires. And what that means is that people can't get out, help can't get in, and again, the critical supplies, they can't move. So that uniquely makes transportation infrastructure both one of the weakest and yet most important links in wildfire resilience. So this figure, or these figures, excuse me, they really kind of reinforce that this topic isn't just like limited to a handful of isolated incidents. So what this shows is that between the year 2000 and 2019, more than 265,000 miles of US roads were exposed to wildfire threats. So to contextualize that a little bit, that's more than 5 times the length of the US interstate highway system and the equivalent to 50 round trips between New York and Los Angeles. And it's slightly longer than the distance between the Earth and the moon. So these threats to roads and rails, the point is they're not rare occurrences. So in regards to our submission, Team CNA's submission, there were two primary research questions that we focused on. Firstly, how can spatial AI be applied to detect and classify wildfire threats using existing data sets near transportation infrastructure or critical transportation infrastructure? So think of like primary roads, like your interstates and highway systems. And secondly, how efficiently can the UNet model segment wildfire threat levels near the transportation infrastructure utilizing satellite imagery and GIS data? And the core deliverables that our project produced included the raw GIS data and labeled training data sets, our pre-trained semantic segmentation model that you'll hear about shortly from Carey, and along with a bevy of documentation just for open source and the repeatability of our analyses. So with that, I'm going to hand things off to my colleague, JJ Huggins, who's going to cover the GIS component of our project and the question for how did we transform the raw wildfire data into something that our model could understand. JJ?
Fantastic. Thank you, Shaun. All right, so to get started, let's discuss our area of interest some. So for our project, their chosen area of interest was Southern California. There's a number of reasons why we chose Southern California as the basis for our project. Specifically, the main reason, though, was the prevalence of wildfires and the impacts of those fires on Southern California. which are notorious and annual. In this visualization, you can see that there are the various counties of Southern California. You can also see some pink polygons underneath, quite a few of them. Those are the historic fire perimeters around Southern California. And this gives some idea as to how extensive and common they are. The callouts that you're seeing here, such as the Thomas Fire, the Palisades Fire, or the Eaton Fire, these are just some major fires that have occurred in the recent past. And some of these fires are also fires that we included within our own training data that were implemented into the project. Next slide. So what is CAL FIRE? The California Department of Forestry and Fire Protection was founded in 1885. It's simply put a very critical statewide fire force of firefighters and analysts and various people who support local firefighters and respond to the most devastating fires in California. They don't just respond to fires, they also investigate the causes for fires. And that graphic that you see there is indicating how the number of arson arrests have more than doubled in just the last 7 or so years. In addition to all of this, they're also one of the foremost sources for verifiable and trusted data on wildfires and the spread of fires. They have significant free data sets that you can access, and you can turn that data easily into GIS-ready layers that can be imported into ArcGIS Pro or QGIS or whatever system you may want to use. Next slide. So why does GIS matter? For our project, simply put, it's critical for creating the AI-ready data sets and training information that's required for the development of our model. Therefore, before any modeling could happen, GIS is what gave us the foundation. We really needed to tie wildfire risk to actual road data and railways in order to assess where the real fire threats were. And that meant working in a spatial manner. So in the graphic that you're seeing below, you're seeing the combination of the imagery, infrastructure, and fire threat data, which were transformed into our training data. Simply put, without GIS, there's no spatial context. That UNet model, which we developed, can't learn where the fire threat classes intersect roads. And unless we first define that spatial relationship through a series of geospatial data processing, there is no training data. Next slide. This is a very quick visual of the GIS process. I'm not going to go into significant depth on this slide, but I will in the following slides. But what you see here we have our major data sources on the left. And these were compiled together through a number of geoprocessing steps, which developed these layers into training data, which would then be used in the export training data for deep learning tool to form the image chips and labels, which formed the real basis for our training data, and helped to give us the ground truth information that was fundamental for checking our model later. Next slide. All right, here's where we're going to get into the process in a bit more depth. So for our GIS data, we combined our road, rail, wildfire threat data into GIS layers, which then would be converted into labeled image tiles, which are what we use to teach our UNet model. So in this top little blob that you see here, we started with CAL FIRE data sets, such as fire perimeters and threat classifications and high hazard zones. From these, we took them and we dissolved their classifications down so that they were only including the extreme, the very high, and the high danger or threat classifications. Everything else, therefore, was basically simplified to no threat. These data sets are then merged, they're clipped according to the area of interest, and required attributes are added for model training. For the roads and rail features, there's a bit of a different process that's required. These data sets aren't built with classification in mind, so in certain situations, you might have road features that span the entirety of California or an entire state. This doesn't make them very effective for detailed classification. In order to remedy this, we decided that the best process was to simply aggregate these line features by their endpoints. We then intersected them, creating points at those intersections, and we split those line features according to where those points were. Simply put, this split the lines into different lines where all of the intersections were. After this was intersected with our CAL FIRE data again in order to provide the classification information to those line features. And then they were resymbolized and provided with a 100-foot or 1,000-foot buffer, which would create the polygon feature, which our training data would be defined by. Moving on to Sentinel-2 data. The Sentinel-2 data can be obtained from the Copernicus browser, and it is GIS ready from the point of download, which is fantastic. It only requires slight modification and maybe some filtering to find the exact resolution out of their folder structures that you would like. For our project, we chose the 10-meter resolution data and clipped it to our area of interest, and then we overlaid our road buffers, and then we extracted according to those road buffers. And that's what formed the basis for our training data. Next slide. So let's get a little bit into some visuals of what that looked like, and also a little bit of the quality control process. What you're seeing here are fire perimeters and the threat layers and high hazard zones and the vegetation, all dissolved according to the simplified threat classification schema, which I mentioned earlier. In the steps 1, 2, and 3, what you're seeing is the overlaying of the classification layer over the previous layer. So you have the original threat layer there, you have the original and the dissolved threat classifications overlaid, and then you have just the dissolved threat layer. So you can see that there's consistency there. These are the outputs of the processes that were explained in the previous slide. And so what's important to note here really is how we're overlaying the dissolved layers, as briefly mentioned, and we're overlaying the road layers over the trusted CAL FIRE data sets. In the visual below, you can note how the road classifications follow and are consistent with the CAL FIRE threat classifications underneath of them. And as you can see here, we have the extreme fire danger, we have the very high fire danger areas, and we have the high fire danger areas. And those are being identified based off of how much of the area covered underneath those roads aligns with a certain threat classification. Next slide. So after doing all of that and checking for the quality, making sure that there's high quality data being fed into our model or being prepared, there's some really minor final steps that are required in order to prepare the attribute information for model training. And that's really what this slide's going through. So what's essential in GIS or in ArcGIS Pro is that you have to add value ID fields into your data for your training to be feasible. And those value ID fields should equate to your threat classification schema, or your schema that you have decided upon for whatever your deep learning project is. For our project, those value IDs equated to 1 was extreme, 2 very high, and so on and so forth. During this process, it was also decided that we should calculate some of the area percentages just to help us validate results later on and understand if the amount of classification of each class aligned with what our CAL FIRE data provided us. Next slide. The final major steps were extracting and exporting the data per each area of interest, which is what this slide is going to go into. As previously mentioned, we used the export training data for deep learning tool, which is a spatial analyst tool in ArcGIS Pro. The main thing to note with this process is, one, it's very straightforward. It's very accessible as long as you have labels and you have imagery data. But it is very time consuming. And depending on the hardware that you are using to do this work, you can see run times of up to a couple hours or as low as 10, 20 minutes, depending on how extensive your labels are and how high resolution your satellite imagery is. Next slide. So now that we have our labeled data, the question is, how do we train an AI to detect wildfire risk? And in order to give you all a very detailed description of how that is done, I'm going to hand this off to Carey, Whitehair-Conde.
All right. So from the machine learning perspective, that labeled images or masks, as we're going to call them going forward, those are semantically segmented. And what that means from our perspective is that every pixel in that image falls into a class. In our case, it's going to be those risk classes, whether it's low, extreme, what have you. It also means that there's no separation between the different instances of a class. So some of you might have seen instance segmentation or object detection, which certain automated vehicles use, where it's able to distinguish between individual people or individual cars. And you can see with semantic segmentation that that's not happening. But the upside of semantic segmentation is because every pixel is labeled, you get a more robust image of your image, so you get the whole picture, and you can handle many classes. So what do we do with that semantically segmented data? If we go to the next slide, we're using that in our UNet model. So the UNet model kind of looks like a U, and what it will do once it's been trained is it'll take in a regular RGB color image in our case, and it'll return the same size image, but it'll, instead of RGB, it'll just be those 5 class colors, which we can then assign whatever colors we'd like to. So how this is working is, going down the UNet, you have these encoder blocks, which are a pretty simple structure of 2 convolution layers and a pooling layer. And what it's doing when it's going down those and increasing the channel size, that 3rd dimension, is it's learning information about the image. It's kind of like zooming in from a really far out image to get a bunch of details or focus on, let's say if you had a forest, then you're focusing on the trees or the details of the bark and how the different trees are related to each other, where they might appear, things like that. So it's learning those patterns, contextualizing the different parts of that image and how those different classes in the future might be interacting. Eventually, you reach a deep enough layer and you're going to predetermine that. And then you are going to start going up, at which point you have those decoder blocks. And again, it's still a pretty simple structure. You're going to have a concatenation where some information is going to get passed forward. that'll be concatenated with the upsampling, which is trying to get it back to that appropriate size, and then the convolution again. So going up, it's taking all those things it learned going down and rebuilding that image, but with your classes instead of the original color image. Now, the most important part of the unit and why it's so successful at what it does is those skip connections. Now, if it only had the ability to do that zoom in and focus, you would effectively lose the forest for the trees. But with the skip connection, you're passing forward some of that zoomed out, larger context image into the upsampling. And so by doing that, you're not losing the forest for the trees in this case. And so why did we choose the unit? Why didn't we choose a different model? Well, units themselves, like I said, are pretty simple structurally, which means they're pretty lightweight. With that lightweight, it means you have an easier time training, you're not running into computation issues as you might with other models. It's also really good on small data sets, again, because of that skip connection, because it can learn those details even if there's really small parts in the image. It learns those details and is still able to pass some of that forward with the skip connection. Also, because of that skip connection, it's good on imbalanced data sets. Looking at our data, which from some of the images that you saw earlier from JJ, you can see that the roads and rails really only take up a small part of our images. So there's, in our case, a lot of background. That data is imbalanced. It means that we have a lot of the background class, not a lot of the road and rail risk classes in an individual image. But that's okay, because the unit can handle that. And then just furthermore, like I said, it maintains that spatial resolution. You don't have to resize anything, and it's learning those small localized features. So now that we know what the unit looks like, we can get into our actual data a little bit and how the unit was trained. So if we go to the next slide, so here we see just an idea of what our data going into the unit looks like. We have the images, we have the masks, which are just different colors from what JD was showing earlier. And in our case, like I said, it's a small data set. It's only 1,000 images, which if you've done anything with neural networks, you know is not a lot of images. Those images in our case are the RGB color images, and then our masks have 5 classes. Important thing to note, one of those classes is in fact the background, which we don't really care about, but it is getting classified. 80% of that data, 80% of those images is going to go to training, 10% to test, 10% to validation. For our unit, we chose a depth of 4 blocks, and we chose that in part because we didn't want too complex of a model, and we wanted to try something that we expected would perform well enough, like I said, without being too complex. In a moment, I'll get into what the optimization function is. In our case, it was atom optimization, and I'll also get into the details of what that loss function is, the categorical cross entropy. For training, we used a number of different metrics. Intersection over union, or IOU, which is just the overlap between the prediction and the true value. We use the dice coefficient, or you can call it the Dice-Sorensen coefficient, F1 coefficient, all the same name for the same thing. And that is a combination of precision and recall. And then again, we're also watching that loss function. Now we watch that for both the training data and the validation data, because with the training data, that's the data that the model is going to see repeatedly. And so we obviously want it to do well on that training data. But we also want to make sure that it's not over specializing in that training data. So it has the validation data that it will run through at the different epochs, at the end of each epoch, to make sure that it's able to generalize. And so we'll see that going forward. Now, what are these epochs and batches? So for our case, we had 25 epochs and a batch size of 8. The epochs is just the number of times the entire data set is passed through the model. So all, in our case, 800 images for the training data. The batch size is the number of samples, so that pair of images and masks that are processed before we update the weights in the unit, before we update those layer weights and things like that. So if we go to the next slide, I can get into the details of what is atom optimization. So atom optimization is adaptive moment estimation optimization. It's got three main parts, which are momentum, root mean square propagation, and it's done per parameter. So to make this a little less abstract, let's consider that we have a hiker who's up in the mountains. Maybe it's a foggy day and he can't really see where he's going that well. And what he wants to do, what he wants to optimize, is he wants to find the lowest valley in that mountain range. He doesn't want to take the longest way to get there. He wants to try and get there in the fastest way possible. So with momentum, what he's going to do is if he feels like he's going in the right direction using that loss function, then he's going to keep going in that direction and he might go a little bit faster. So he knows where he was previously and he thinks he's going the right way, he's going to go faster. What root mean square propagation would be like if you were adjusting based on the terrain. So if the terrain is really rough or unpredictable, maybe he's going to take smaller steps. If it's really smooth terrain, like a paved path, then maybe you can take bigger steps. The per parameter component of adaptive moment estimation is just that the RMS propagation and momentum are going to be applied per parameter. So, for example, if going north to south for the hiker was really rough terrain and he wasn't sure if he was actually going down or not, then maybe he would slow down a little bit north to south. But maybe east to west, it's a paved path, he can see that it's going down, there's a little bit of clearing in the fog or something, then he's gonna go faster and take those bigger steps. So he adjusts per parameter. So how does he actually know if he's going in the right direction? That's going to be the loss function. So the example I have for the loss function is if we pretend this set of squares is a pixelated image and each pixel has a class. So in the upper right-hand corner of that pixelated image, we have that pixel is the class, the third class. In the true case, that means it can only be the third class. Our classes are mutually exclusive. You're not going to have a pixel that is both 2 and 3 or something like that. It's only ever going to have one place where the true vector is 1, right? In the predicted case, however, it's going to be sort of a probabilistic distribution. So in the prediction, it is most likely a class 3, and eventually when the unit actually outputs something, you apply a threshold and things like that. But we use that probabilistic prediction to calculate the loss. So if you're looking at this and if you're familiar with log functions, you know that as the log gets closer to 1, then the log of that value is going to be 0. You can also see that because we have distinct classes that are mutually exclusive, the only value that actually matters from this calculation is the very last one. The other ones are always going to have that preceding 0 because of the true vector. So then we calculate it, and that's how we get the loss. Now, the important thing to note here is that this example is just per pixel. In reality, for the whole image, when the unit is being trained, it's averaging across all of the pixels. And you'll have this for all of the different classes. So now that we have a grasp of how the unit works, what it is and how it's trained, we can actually take a look at what our output is on the next slide. So on this slide, this is just if you were to run our model, this is some of the things that you would see. The first thing I want to point out are the red boxes. So you can see in the red box in the upper left, that is the image size. It's 256 by 256 by 3. The preceding none value that you see for all of these is because this is just the model itself. There's no images that are already in the model. This is just, hey, here's what the structure of your model is going to look like. So you have an idea that everything is built correctly. The red box in the bottom right is 256 by 256 by 5 because that's the number of classes that we have. So it should be outputting the correct mask. The only other thing I wanted to highlight from this structure is that you can actually see the skip connection. So that's what those dashed blue boxes are. You have the initial output from the convolution from that one encoder block. And then when you are upsampling, you can see that that skip connection is coming forward and it's being concatenated with the upsampling. So I just thought that was neat that you could actually see the structure of your unit output correctly. In the bottom of this is just what you would see while the training was running. Like I mentioned, we have those different metrics that we're watching for both the test data and the validation data, and that's updating every epoch. And so, as would be expected, we can see that our coefficients are improving and the loss is also improving through those. But if we go to the next slide, we can see that a little bit more clearly. So these are the results of training on the 800 images, validating on 10, and over 25 epochs. We can see that as the number of epochs increases, we're getting better results. But the important thing to note is that we do start to see a bit of separation between the training and the validation. Now, this is what I was talking about before, where because we see that separation, we know that our data is learning that our model is learning that training data very well. It's improving, it's doing great, but it's becoming over specialized and it's not able to generalize what it's learned to the validation data. So that's why we see a little bit of that separation. That is something that in the future we can train for and tune and play around with our model, but it's an important thing to note. If we go to the next slide, we can see the results. This is probably a little bit more visually intuitive than just some lines going down. So we can see our original images, our original masks, and then the predicted masks. We can see that it's doing pretty well. And just in this small subset, we can see that we have predominantly extreme risk and high risk. Now, if we look over to the numerical results, there's some important things to point out. Very briefly, precision is just like a confidence interval for the model. So if it predicts that a pixel is a certain class, then it's right. So precision is penalizing false positives. Recall, however, is sort of what helps us see if a class is being missed by the model. So what that means is it's sort of penalizing false negatives. The model just isn't seeing those classes when it's going through. So we can see that apparently with the low to moderate. When it predicts a lower moderate risk, it predicts it correctly. That's why the precision is higher. However, when there is lower moderate risk in an image, it's not likely to identify that even though it's there. So that is in part because our data predominantly had the high risk and the extreme from high to extreme risk. We had fewer images with that lower moderate risk. So that would be something for us to account for in the future. However, we can see for the extreme risk that the precision and recall are both about on par with each other. And some of this can be improved with more data. So on the whole, we're seeing pretty good results from this unit, particularly with very few images and very little tuning of the unit itself. So here in a moment, we can go forward and we're going to talk a little bit about the conclusions and the applications of our results, both from the unit, but also from the GIS side. So I will let my colleagues take it away.
Thank you, Carey. Fantastic. So to conclude, GIS tools are how we validated our results against the CAL FIRE data sets. And the geospatial accuracy of our layers was assessed through georeferencing, and the prediction classification accuracy was then also checked through overlaying the data to identify inconsistencies between the result masks and labels. This was done using a very simple model, which is visualized here. That model, simply put, would define the projection to the specific Southern California region we were working in. So that would be WGS 1984, UTM Zone 11 North, or for most of our data. And then it would convert our raster overlay into a vector and then overlay those results with the labels, allowing them to be easily compared, which is what you're seeing in the visuals here presented to you on the right. We also did some further visual inspection. The reason for that is that Sentinel-2 is a push broom sensor, and you have overlapping images that are organized all together. And so whenever you are sorting through this data, sometimes you can get imagery that's nearby, but from different images and therefore different times. So sometimes it's relevant to check what your actual raster data is showing. The prediction masks that were produced matched our image chip locations exactly in terms of georeferencing accuracy. And the classification results overall were pretty high accuracy from the random sample of about 100 that were checked. And furthermore, the model was developed to preserve the integrity of the spatial information throughout the training process and developing the results. And so that allows for very easy transportation into GIS or remote sensing softwares. Therefore, because of that preservation of the GIS information, we can simply drag and drop or import this data into a variety of softwares, including ArcGIS, QGIS, ERDOS, SocketGXP, or the European Space Agency's SNAP application. We're confident too that that models such as ours hold some value to various real-world industries. Those are including but not limited to supply chains and disaster response or first responders, insurance companies, and more. Really, we also have future kind of advancements that we're planning for this project that will probably improve this model's ability to actually provide on-demand results and be deployable. But at this time, obviously, it's probably still requires some work before we would be willing to deploy it in that manner. So yeah, I'll hand it off to our other colleagues.
So again, from the unit perspective, it performed pretty well on a relatively small data set with a relatively short training time. So we have further details on our webpage on the I-GUIDE site, but when I say short training time, what I mean is that it took between 5 and 8 hours on a low to mid-tier laptop training that data. And that's not a lot of time for data training at all. And again, it was on a pretty small data set with only 1,000 images. So we're pretty happy with these initial results from the unit. Obviously, it was performing better on the higher risks, in part because those were more prevalent in our data set. So we know that there's improvements that can be made on the unit model, but once it's been trained, then deploying it, if it has seen enough of the appropriate data, is very easy and straightforward. You pass in whatever your images are in the correct RGB format, and it can spit back out that threat level or those risk classes for any given image that it sees. So I think we're pretty happy with the unit, and we look forward to making some of those improvements. We'll actually talk about some of the future plans we have and what we'd like to do on this next slide. So from the unit side, the obvious ones are, let's get it more data, let's get it a variety of data. And because we do have a number of different data sets from CAL FIRE available to us, it would be good to combine some of those data sets so that the unit is getting a bit more of that variety in what it's seeing and training on. Another thing which I didn't really touch on earlier is we used intersection over union and the dice coefficient, which are suitable initial starting points for watching the data and seeing how well it's training. But there may be better metrics, such as Tversky and focal, in part because our data is imbalanced not only in an individual image, like I mentioned, more background versus our risk classes, but it's also imbalanced in terms of which risk classes we're seeing. So those evaluation metrics might be better able to identify those challenges. Another thing that we should certainly do is adjusting some of our model parameters. So we played around a little bit with the number of epochs and the batch size, and some of our optimization parameters, but we could certainly do more to tune our unit model. We could even consider it, making more updates or even changing out our optimization function to see how that improves the model. I'll let my other colleagues talk about how we're going to hopefully expand this research.
Yes, and thank you, Carey. So one of the consistent themes throughout today in this presentation has been the overall structure and design of our project. It was a little smaller in scale to allow for us to really be able to move as efficiently as possible, given some of the computational constraints and resource limitations that we encountered. And despite it being smaller in terms of like the data size, the impact of these preliminary and initial results were quite substantial, to the point of encouraging us to considering how to scale up the capabilities and really bolster up our model and analyses capabilities. And so in that sphere and on like the GIS in the spatial realm, and in considering the potential real world impacts and applications, one area that we're interested in exploring is incorporating new geographic regions. When we kicked off today's presentation, the map that we shared noted how really concentrated wildfire threats can be in Western states, but still with tendencies to distribute across the country and have the type of impacts that this model is able to identify, um, and, and identify and help responders and planners and stakeholders address in a proactive manner. And so to do that, we would consider incorporating other geographic regions such as Texas and California. And we know wildfire threats aren't just limited to the United States. It's a global issue with clusters all across the world. In addition to that, we are considering opportunities to incorporate this into other tools and other forms of assessments that can take into account total risk and threats for transportation infrastructure, in light of like other forms of extreme weather, so like flooding events, for example, or hurricane related events. And finally, just considering the inclusion of additional accuracy assessments to ensure the positional and logistical consistency of our results. So in other words, the reliability of what the UNet is able to produce and ensuring that it meets the real world and ground truth realities. So with that, that concludes our presentation for today. I see that we do have a few minutes remaining, so I can certainly open the floor for any questions that anyone in the audience may have for the team as a whole or any specific individual. And if there are no questions, can hand things back off to you, Anand.
Yeah, any questions? I think this was great presentation. Thank you. Any questions for our speakers?
So I do see two questions in the chat. One regarding the recording. So Anon, I'll let you handle
Yep.
that.
Yes, the recording for this session would be available on the I-GUIDE website. Maybe in the next 2 days, I'll post a link there in the chat in a momentarily. But yeah, it should be available. And previous recordings of the VCO sessions are also there.
Yeah, and for the other question, I think there was, regarding the slides. Anand, we can touch base with you offline about that and, provide you a copy of them to disseminate.
Yep, that would be wonderful. Thank you.
Okay. Okay, and I do see another question regarding, and the question states, could you please elaborate further on how insurance companies or the Postal Service might use the results in your study? So before I answer, I know this was something that really resonated with JJ. I'm curious if you have any comments that you'd like to provide to that.
Yeah, sure. So currently, insurance companies use a number of analytical methods in order to assess fire danger and in order to predict pricing for insurance rates. And this is especially true in states like California. Fire insurance is incredibly expensive in Southern California. It's not a stretch to say that it could cost more than a year's salary for your average American. And those sorts of assessments are done with similar means. They have a number of deep learning or artificial intelligence models that they use in order to assess a whole variety of different aspects of climate or wind and other things that might impact the spread of fire or the danger of fire to different regions. And so along those lines, this tool would likely be used in order to support similar predictions and would probably just support already existing analyses that are present. The Postal Service idea came out of the Palisades and Eaton fire, specifically because if you look into those fires, you'll find that there was massive blockages to all sorts of supplies, but Postal Service was one of those where you had firefighters blocking various neighborhoods off for multiple days, and due to that, and due to also the impacts of the fire and the blocks caused by that, there's major disruption across a variety of different supplies, but one of those being mail. And so we figured it really was put in at the very end also just because we're not sure that they would possibly employ that, but it seems that it might have some inherent value to services like that.
Exactly. And just to kind of put a bow, excuse me, on JJ's response, this tool, especially once we get it like refined and like fine-tuned, our expectation is that this will provide segment level threat assessments for transportation infrastructure. So that could be extremely valuable for routing analytics and logistics. So within that space is why we think it could be beneficial to clients like the Postal Service to help them potentially have another resource to navigate terrains, because we know the Postal Service tends to run 24/7 throughout all types of conditions, as we've seen in reports and in media and so forth. But just for them to have another tool to be able to guide them to navigate their routes as safely as and well informed as possible, driven by data that our model can help produce. So I don't see any other, you're welcome. So I don't see any other questions in the chat. So I
Yeah.
would just like to take another moment. I want to thank Carey, JJ, for your hard work throughout this project. It was an amazing job with what we developed along the way. I'd like to thank you, Anand, and the entire I-GUIDE community. This was a very fun experience, and it challenged us and allowed for us to develop a wealth of capabilities that we've applied in a number of different ways in our organization on other projects. And I think that that's only going to continue moving forward with some of the capabilities that we really kind of developed over the course of this challenge. And for those of you who might be considering taking part in future I-GUIDE challenges, I would emphatically encourage you to do so. This was just an amazing experience from start to finish. And finally, just thank you to everyone for taking some time out of your schedules to attend this presentation today. I hope that it was informative and of value to you all.
Thank you so much, Shaun, for nicely concluding this. This is wonderful presentations, going into all sorts of details, and I'm sure the audience enjoyed it and will post it. And we have lots more people watch through this. As you said, this was a wonderful experience for us as well, for learning from CNA group. Like this was our first attempt working outside the academia, and that was wonderful. We learned a lot as well. So thank you for that. The other thing you mentioned was future I-GUIDE challenges, and I would say that we would be running another challenge, and more details on that would be posted shortly. But like I think we will have another spatial AI challenge, 2025 edition coming out soon as well. So look forward to that, and look forward for participation from all of you on that as well. Thank you so much for taking the time, and we'll see you next week on another virtual consulting office session. Thank you all. Yep. See you. Bye.